Argon. Yes, sir. Yes, sir. 4s0, 3d8. Correct? Huh? Say something. So I am writing it as 3d8, 4s0, and 4p also 0. P possess 5 degenerate orbitals, and S and P 3 degenerate orbitals. Now I have started filling electrons 1, 2, 3, 4, 5. As cyanide is strong field ligand, all the electrons need to pair up. If all these electrons pair up, what happens? 1, 2, 3, 4, 5, 6, 7, 8. Now this d orbital becomes empty. And how many ligands are there? 4. 4 ligands means what should be the hybridization, sir? Now DSP to hybridization. If it is DSP to hybridization, geometry square planar. Square planar. Now tell me whether it is low spin or high spin complex. Paired up. Yes, low spin complex. Magnetic moment mu or mu s. Mu s is 0. Diamagnetic complex. Mu s is 0, mu b. Diamagnetic. Next example, sir, what they give? Next example, sir. Or in your target booklet, what is the next example they gave? CO, NH3 6 times. CO, NH3 6 times plus 3. Yeah? Now here cobalt is in plus 3 state. What about ammonia? Strong field, and remember, special case, sir. Very, very, very important point. Very important point. Sir. అవును సార్ చెప్పండి పర్లేదు. అంటే మన బయట ఉందా మన వాటేనా? Right. Here one note, sir. Very, very, very important point. Yes, sir. So many disturbances. Always in my class only. Huh? See this note. Particularly in cobalt plus 3 complexes, sir. In cobalt plus 3 complexes. Generally, ammonia is a strong field ligand, right? Not only ammonia, water and oxalate C2O4 2 minus. Can I write as oxalate or not? C double bond O minus, C double bond O minus. Oxalate ion or not? Right? Also behave as strong field ligand. Special cases, sir. Right. Right? In cobalt plus 3 complexes, generally water and oxalate which is donor, oxygen is donor, na? If oxygen is donor, we have to consider them as weak field ligand. But in case of cobalt complexes, they are to be behaving as strong field ligand, special case. That's why we have taken it as a note, right? Now come back to this. Now here, what is ammonia? Obviously, strong field ligand. If it is strong field ligand, what should happen? What should happen? So what is the atomic number of cobalt? 27. Means 4s2 3d7 plus 3 state means 4s0 3d6. Correct, sir? So argon 3d6 4s0 4p0. Right? Now D. 5 degenerate orbitals 1 2 3 4 5 s1 p3. D6 means 1 2 3 4 5 6. Now tell me how many ligands? 6 ligands now? Response, sir. So what is the hybridization? C2sp3. So geometry octahedral. Now observe carefully. For hybridization, do inner 3d orbitals are involved or outer d orbitals are involved? That's why we call this complex as inner orbital complex. Are you able to understand? Right? 3d belongs to inner orbit. Outermost orbit is 4s, 4p and 4d. Instead of that, d orbitals of 3d is involved. Right? So we call this as inner orbital complex. Low spin or high spin? Mu. Therefore, it is. Any other example given? Any other example they have given? That's all. Huh? CO F6. Huh? Okay. CO F6. This also 3 minus. Huh? Cobalt is plus 3. Now tell me, sir, what is fluorine? What is fluorine? Weak field. Weak field ligand means I should not pair the electrons. Here also cobalt is in plus 3 state. Again, I have to write argon 3d6. Observe very carefully. 4s0, 4p0, 4d0. In case of 3d, degenerate orbitals are 5, 1, 2, 3, 4, 5, s1, 3, p, and d again 5, 1, 2, 3, 4, 5. Now d6. Now observe, sir. As this is weak field ligand, I should not pair up. So 1, 2, 3, 4, 5, 6. Now every fluorine donate electrons. So I need empty orbitals. How many empty orbitals are required? Satisfied? Now tell me hybridization, sir. Not D2sp3. sp3d2. Geometry. Octahedral. Now is it inner orbital complex or outer orbital complex? Yes, outer orbital complex. Low spin or high spin? High spin. Pairing doesn't happen, so spin value is high. Number of unpaired electrons, 4. So root of 4 into 4 plus 2. So root 24 Bohr magneton. Correct? Paramagnetic. Any questions, sir? Is it clear? Respond. Any questions in this?
No, sir.
Right. And you need to remember these two. In case of cobalt, if I consider water or oxalate, then also I have to consider them as strong field and I need to do pair. Right? Right? Now, limitations of valence bond theory. So we are done with valence bond theory. Now, limitations of it. Limitations of VB theory. First one. For few complexes, it is paramagnetic. For few complexes, we are saying diamagnetic, right? How we are doing paramagnetic or diamagnetic? By saying pairing electrons or not pairing electrons. And sometimes I have taken water as a strong field. Some cases I have taken water as weak field. Correct? Why I have to consider water as strong field? Why I have to consider water as weak field? No explanation. Are you able to understand? We took it as an exception. Why it has to be taken as an exception? There is no explanation. That is the first demerit, right? So unable to explain. It is unable to explain magnetic properties. Unable to explain magnetic properties. Why few complexes are colored? Why few complexes are stable? Whether they are kinetically stable, whether they are thermodynamically stable, no explanation by using valence bond theory. First limitation. Second limitation. If when coordination number is 4, in few cases we have taken square planar, in few cases we have taken tetrahedral by saying strong field or weak field, correct? But valence bond theory never said this is strong, this is weak, here pairing should not occur, right? We will see final magnetic moment data. Based upon the magnetic moment data, as it is diamagnetic, we are pairing it, saying it is a strong field ligand. If it is paramagnetic, unpaired electron should be there. As unpaired electron should be there, I am considering that ligand as weak field ligand. By observing all that experimental data values, few cases by observing different ligands, we made to a conclusion when carbon and nitrogen are donors, they are strong field. Remaining cases, they are weak field. That conclusion we made based upon the experimental magnetic moment values. Are you able to understand? But valence bond theory has not given any explanation for it. Understood? Any questions in it? Response, sir. Right? So geometry was not interpreted properly. Point 3. Why same ligand sometimes considered as strong field, sometimes as weak field also? There is no explanation. So ligand field strength was not explained by valence bond theory. These are the limitations. To explain about this field strength, next theory was proposed. The name of that theory itself is ligand field theory. We also called as CFT, crystal field theory. We call it as ligand field theory, right? In order to explain stability of complexes. The same theory is also be named as crystal field theory, CFT. Ligand field theory, crystal field theory, both are same, no difference. All right. Now, once open your target booklets. In ligand field theory, first you will find some postulates. Ligand field theory, you will find some postulates. So let me see that postulates. Postulates. Point 1. Ammonia is a ligand. Is it positively charged or negative or neutral? Neutral. Neutral molecules or neutral ligands are considered as point dipoles. Yes, sir. Both are same only, man. There is ligand field theory. Both are same only, man. Right? Only difference is in ligand field theory, we will discuss about spectrochemical series. That I will include here itself. right? Response, sir. Okay. You want heading crystal field theory? Yeah? Okay, I will write it. Crystal field theory. Done? Right. Now listen. Now, according to this theory, ligands are considered as point charges. They are considered as points, right? If they are neutral molecules, they are considered as point dipoles. If they are negatively charged, they are called as point negatively charged point charges, right? There is no explanation about positively charged ligands. Limitation, right? So what postulates was done by crystal field theory is ligands are considered as point charges or point dipoles. Ligands are considered as point charges or point dipoles. If they are point dipoles, means they are all neutral molecules. If they are point charges, means they are negatively charged, but there is no explanation about positively charged ligands, right? Now, second, all the interactions between central atom and ligand is considered as ionic interaction, right? Or electrostatic interaction. But till now, what we discussed, ligand will donate lone pair, central atom will donate empty orbital. Valence bond theory, man. In valence bond theory, ligand donates lone pair, central atom will donate empty orbital, involved in coordinate-covalent bond formation for getting hybridization geometry. Correct? But according to crystal field theory, all interactions are ionic interactions, or we call it as electrostatic interactions. Ionic bond is also called electrostatic bond, right? All interactions are considered as electrostatic interactions. Means there is no covalent bond formation. Correct? Huh? Means no overlapping or intermixing. If it is overlapping, valence bond theory. Intermixing, hybridization. Atomic orbitals of nearly same energy will intermix to form hybrid orbitals. That is hybridization concept. So there is no overlapping concept. There is no intermixing concept. Point number 3. Now, when central atom is present, around central atom, electrons are present three-dimensionally, right? When ligand approach, ligand also having electrons. When ligand is approaching the central atom, the electrons of ligand, the electrons in the outermost orbit of central atom, both will repel, right? When they are repelled, the electrons of central atom will be aligned in such a way, they will try to occupy less space. If we consider this as central atom, all electrons are symmetrically distributed through in all directions. When ligand is approaching, ligand electrons are present. These electrons will repel these electrons. When they are repelled, what about electrons around central atom? They will be occupying less space or not? Right? They are not present in this direction now. They will get adjusted into remaining space. In that way, if other ligand is also approaching, then again another ligand. When there is repulsive forces, what happens to energy of electrons? Increases. Correct? Respond. When energy increases, the orbitals which are present in the direction of ligand will experience more repulsions compared to other orbitals in other directions. For example, one ligand is approaching along x-axis. Then the electrons which are present in d orbitals in x-axis will feel more repulsions than compared to d orbitals which are present along y-axis and z-axis. Is it clear? Means degeneracy of d orbitals is lost. Right, what we discussed till now, according to valence bond theory, electrons are redistributed among d orbitals. Pairing happened. Sometimes pairing are not happened, but we call them as degenerate orbitals. No, all 5 orbitals of d are having same energy. But according to crystal field theory, when ligand is approaching, the d orbital which is present in that direction is experiencing repulsion, Means what about remaining d orbital electrons? They are not experiencing same. So energy is different now. That means orbital's degeneracy is lost. Is it clear? So due to field produced by ligands, due to field produced by ligands, is not symmetrical. If it is not symmetrical, what happens to degeneracy of d orbitals? Degeneracy of d orbitals. What happened? Degeneracy of d orbitals is lost. When degeneracy is lost, the d orbitals which are along the axis will have different energy compared to d orbitals which are between the axis. How many d orbitals are between the axis? 3, dxy, dyz, dzx. Only 2 orbitals are along the axis, dx square minus y square, dz square. So dx square minus y square, dz square will experience different energy. Remaining 3, dxy, dyz, dzx will experience different energy. Right? That's how we will say degeneracy is lost. Now I am writing that in a diagrammatic way. Right? Assume these are the 5 degenerate orbitals. Assume these are the 5 degenerate orbitals. If you want, you can name it also. dxy, dyz, dzx, dx square minus y square, dz square. Now, when ligand is approaching, what happens to the electrons of ligand and d orbital electrons? They will repel because of the field which is around the electron cloud of ligand. Right? Because of repulsion, what happens to net energy of this? Increases. So as net energy is increased, can I write like this? Will you understand what I am trying to write? Will you understand or not? When ligands are approaching, the energy of those orbitals enhanced. Response, sir? Will you understand the meaning of it? Now tell me, when energy of orbitals enhanced, do all the energy of orbitals remain same or they have separated now? They got separated. This is the energy of them. The electrons, what I have done, when ligands are approaching, they are feeling repulsion. When they are feeling repulsion, their energy raised. But all d orbitals will not feel the repulsion equally. Few orbitals will feel more repulsion, few orbitals will feel less repulsion. But we know that energy can neither be created nor destroyed. Means I need to redistribute the energy between them. The orbitals which are not feeling repulsion, their energy should decrease. Orbitals which are feeling repulsion, their energy should increase. The energy lost by the other orbital should be given to the orbitals which are getting that repulsive field. Are you able to understand? Overall, there are 10 electrons. Assume 4 electrons are feeling repulsion, then 6 electrons are not feeling repulsion. Then energy of these 4 electrons should increase. From where I have to give that energy? By removing that energy from these 6 electrons, we will transfer that energy these to 4. Or I will distribute the energy of these 4 electrons among these 6, and energy of these 6 will be distributed among these 4. Then what happens to net energy? Are you able to understand? In d orbitals, totally how many electrons I can accommodate? 10, right? In the 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? What I will do is, energy of these 4 electrons will be given to these 6. Energy of these 6 electrons is given to this 4. Now what happened? Net energy. Energy can neither be created nor destroyed. So we are not bringing any energy from outside. But what happens to energy of these 4? 6 electrons energy is given to 4 means each electron will get more energy now. 4 electrons energy is given shared between 6 means their energy decreases. Means that's how degeneracy of all the 5 d orbitals is lost. Clear? Any questions in it? Now I am writing it. So this is orbitals which got splitted. When I am splitting, is it clear, sir? What I have done? Dx square minus y square dz square dxy dyz dzx. Now tell me in which direction ligands are approaching central atom by seeing this splitting. By looking at this splitting, tell me in which direction ligands are approaching, along the axis or between the axis? Because only 2 orbitals are along the axis. So ligands are approaching central atom along the axis, right? We call these 2 orbitals are Eg orbitals, doubly gerate. These orbitals as T2g orbitals, triply gerate, right? T2g orbitals, Eg orbitals. Now the energy gap between them, should be written as delta naught. The energy gap is given as delta naught, right? This type of splitting happens in case of octahedral complexes. This type of splitting occurs in case of octahedral complexes. Why, sir? Observe the shape of octahedral complexes, man. There is xy plane. Among xy plane, 4 orbitals are there. Along plus x axis, minus x axis, plus y, minus y. One above, one below. Z axis means 6 ligands will be approaching along all the axis. 6 ligands are approaching along all the axis means dx square minus y square dz square. All lobes of dx square minus y square dz square will feel repulsion. Remaining all the 3 are between the axis. No, they will not experience repulsion. Therefore, their energy decreased and these energy increased. Right now, how much energy these 2 lobes will get or gain, or these 4 electrons will gain? How much energy these 6 electrons will lose? What is this one? This is the energy of this. Correct? Now, how much energy gained by them? How much energy lost by them? And if delta naught is the gap, right? Delta naught is the gap. If I add energy of these 4 lobes and these 6 lobes, it must be equal to delta naught or not. So what I am doing is, energy of these 3 is given to this. So can I write this value as plus 0.6 delta naught and this value as minus 0.4 delta naught? Accepted or not? Response, sir. Check. Plus 0.6 delta naught. How many electrons I can fill? 4. 4 into 0.6. 2.4 delta naught. Here, how many electrons I can fill? 6 into 0.4. Net over. Net becomes equal to 0. Response, sir. Any questions in it? Right? Or I will think in this way. Can I write the energy of this is 4 by 10. Energy of this is 6 by 10. Give that 6 by 10 to above. Give that 4 by 10 to below. Then note what is the net energy? 0. That's what I am saying. Right? Or think in this way. Totally 5 lobes are there. In that 5 lobes, 2 lobes energy is given to 3. 3 lobes energy is given to above. If 3 lobes energy is given here, then what is the energy of it? 3 by 5. What is 3 by 5? That's what I wrote. Clear? Any questions, sir? Sometimes I will write this delta naught as 10 dq also. Because totally how many electrons I can accommodate? 10. Every electron will have certain energy. That energy I am assuming it as dq, small energy. Sum of all that energy is equal to delta. Clear? Any questions in it? So I'm writing that delta naught as 10 dq. That 10 dq again I have to take in this way. So then what is the energy of this? 6 dq, 4 dq. Okay, minus 4 dq plus 6 dq. Some energy, man, whatever may be the energy. It can be any array. Do we know electron's energy? What is the energy of electron present inside an orbit? We don't know. What we have done? We made one assumption. When that electron is present at the surface, its energy is 0. When it is going inside, its energy decreases. So when it is in first orbit, it has lost an energy of minus 13.6 volts, minus 13.6 electron volts. So what is the energy of electron here means? We are saying it as minus 13.6 electron volts, but we don't know what is the energy of electron there. Whatever it is, its energy is minus 13.6 electron volts compared to the electron which is present on the surface of an atom. Same way, we don't know what is the energy of electron here. If its energy of electron is something, then that energy gap is 10 times of that energy of electron. Are you able to understand? Any questions in it? Understood? Right. This is in case of octahedral complexes. If it is tetrahedral complex, ligand should approach between the axes. If they are approaching between the axes, energy of these 3 should increase, those 2 should decrease. But how many ligands are approaching to form tetrahedral complexes? 4. Then what about this energy gap? More or less? Less. Correct or not? Here 6 ligands are approaching, therefore this energy gap is high. When 4 ligands are approaching, then energy gap should be less. So I am writing that energy gap as only this much energy gap, and I am writing that as delta T, and I call that as a tetrahedral complex. Respond, sir. So for tetrahedral complex, how I will write now? How I will write now? What I have to write here? Above 3, below 2. Now to differentiate, I call this as E, this as T2. Now what is the energy gap from here to here? Don't write G, right? If I write G, what is the difference between this and this? T2G is the energy of these 3. Here also if I write T2G, do they have same energy or different energy? Then how to differentiate them? Are you able to understand? That's why we are representing that as a T2. What about this T2? How much energy more? Plus 0.4 delta T. Correct, sir? This one minus 0.6 delta T. Are you able to understand? Don't get confused, sir. Let me write this a little this side. And in our target booklet, they have written both separately. Here we are writing everything at same place. That's all. This is plus 0.4 delta T. This is minus 0.6 delta t. Now compare delta t and delta naught, which is higher value. So delta t is experimentally when you calculate it, its value is found to be 4/9 times of delta naught. Delta t is 4/9 times of delta naught. When you have taken same ligands, are you able to understand? Same central atom, or if I am taking nickel, right? Same ligand I am considering. Maybe ligand is water. When nickel is surrounded by 6 water molecules, when nickel is surrounded by 4 water molecules, then only this energy gap should be. Don't take different ligands and don't say that delta T equal to 4/9 times of delta naught. When central atom is same, ligands also same, coordination number is 4 here, coordination number is 6 here. Forming tetrahedral complex here. Forming octahedral complexes then, right? Now, one more thing. There may be complexes where number of ligands approaching is 4 only, but geometry can be square planar. If it is square planar, do these two dx square and y dx square minus y square dz square, do they experience same or they also will experience different? Or if I am taking square planar geometry, square planar geometry means 4 ligands should approach only along x and y axis. Z axis becomes free. Then orbitals which are present along z axis should experience less repulsions. Means that dz square should be experience less repulsions compared to, means this EG has to split again. Correct or not? Now among dxy, dyz, dzx, among dxy, dyz, dzx, which will experience more repulsion? Dxy reasonably better than yz and zx. Reason? Plane is xy only, but not along xy, x square and y square, not along x and y axis, but between. But to some extent, they will experience some repulsion, no? But less than dx square minus y square. Is it clear? Online. So, in case of square planar complexes, in case of square planar complexes, those orbitals will split further, right? Now, when they are splitting further, again, there should be a question. Number of ligands are 4 only. Here, number of ligands 6. Correct or not? When there are 4 ligands, do the gap is high or low? And when only 4 ligands are approaching, generally what we think? Repulsion should be low. Only 4 ligands are experiencing showing repulsion. Here 6 ligands are showing repulsion, no? But when 4 ligands are approaching, central atom will pull those 4 ligands closer to it compared to when 6 ligands are approaching, because all the 6 ligands will repel each other also. The central atom is there. 6 ligands are approaching. Every ligand is having its field, right? Every ligand is having its field. 2 the ligands can come closer to the central atom more readily when 6 ligands are there. When 4 ligands are there, they can come closer to the central atom. Reason? Less number of ligands, less number of interelectronic repulsions also. Is it clear? Respond. This is possible only in case of square planar complexes. That's why, of course, it is not given in our target booklet, but observe this. Splitting energy. Can I call it as splitting energy? T2G EG gap is there, no? I call that energy as splitting energy in square planar complexes. Okay. Try to understand. See, check it. What it is saying. This is a delta naught. Means this is a splitting energy gap between. They wrote EG, T2G or not? Octahedral. Now observe. In case of square planar complexes, do this top and bottom energy gap is high or not? Say something, sir. Yes or no? Right? Okay, man. I understood. I have to write. So this dx square minus y square I am writing here. This dx square minus y square. Then what I have to write? Dz square here. Can I write? Say something, sir. I will write dz square here. This is dx square minus y square. This is dz square. What about dxy? Response are correct or not? And what about here? Remaining both dyz and dzx. Now, energy gap. Let me call this energy gap as delta 1, this as delta 2, this as delta 3. Delta 1 plus delta 2 plus delta 3 value is, can I write as delta SP? Or say something, man. Correct or not? No. What is the energy of this? This is approximately, they gave now 1.23 times of delta naught. Or compare it to delta naught. 1.23 times of delta naught. What about this? 0.23 delta naught. This one minus 0.43 delta naught. This one minus 0.51 delta naught. Now add 4 into 0.51 delta naught. Here I can accommodate 4 electrons now. So what is 4 into 0.51 delta naught value? Minus 2.04, correct? Now here 2 into minus 0.43. Minus 0.86. Net value 0, 1, 9, 2.90, correct? Huh? Now above 1 into 1.23. Sorry, 2 into 2.46. 2 into 0.23. 0.46. 12, 9, hey, 2.92 I got. Difference I am getting, man. Something is not matching what it is. With point, whether it is 0.51 or not. 0.86, 0.51 into 4. But it is not fitting, right? Values are not fitting, something wrong. Here also they give delta SP. Array, whatever I give, they wrote in this way. Delta 1, delta 2, delta 3, delta SP. That's all. They have not given that value. They also escaped from that ambiguity. 1.23, 0.23 minus 0.43. Then net must be equal to now I understood. 1 minute. Let me tell you why it is deviating. I want delta SP value with respect to delta O naught. So splitting energy in terms of how we can write in terms of octahedral. They have not given any value. I want delta SP equal to how much into delta naught? I wrote delta T equal to 4/9 times of delta naught. Na? If I know that delta SP equal to how many times of delta naught, then only it is possible to calculate. Because all those individual orbital values we have written in terms of delta naught. But that is in terms of delta SP. Na? If it is in terms of delta SP, it is 0. Not in case of delta naught, right? Are you able to understand? No, that value I want. Definitely, I might have discussed this too. I forgot that value. So repeaters I might have discussed. Coordination, compounds, power step. All right. See, is there any delta SP equal to? Not there, huh? Not there. Delta SP. Not there. Any of you search in net at least? How many times delta SP in terms of delta naught? Online. Someone said, sir, delta SP in terms of delta naught. Yes, sir. Anyone found? One 1.32, 1.5. This one only, right? Square planar. This is double hump, okay. Five to 10% they are saying. Anyone online? Anything, sir?
Sir, it's 1.3 to 1.5, I guess.
Everywhere they gave the same 1.3 to 1.5. Huh? I want that accuracy. Here also not given. In our target booklet, check. 1.74 minus 0.46 minus 0.4 minus 0.9 are relative to Barry center, the average energy of the 5d orbitals. When compared to Barry center, you check 1.74 into. Oh, let me write that values. 1 minute. Let me write that values. 1.74. 0.46 minus 0.4 9.9. Here there will be 2. Here it is 1. Here it is 1. Here it is 1. Now check. 2 into this means this is 3 point. 3 point. Into 2 man. 4 2s are 8. 14. This one 0.92 net 3.4. 4.4. This one 0.8. This one minus 3.6 minus point minus 4 point. Perfectly it is fitting. What is the difference? Now it is fitting perfectly. Check any other way in any other site. Delta SP is approximately 2.64 times of delta naught. But in different sites, they have given different values. How can we conclude? You asked AI, yeah? Any other? Here on, I can also use. I can also ask once. Splitting energy in square planar complexes with respect to octahedral complexes. Hey, what it is giving? May include mistakes. It itself is saying I can do mistakes. Huh? Delta SP is approximately 1.3 times of delta naught. It accepted me. 1.74 times, huh? Everyone is giving different values, means what I have to do? Obvious behavior. The relationship delta SP is 1.3 times of delta. It accepted my statement, man. Delta SP value is approximately 1.73 times of delta naught. That's what it is saying. It is roughly. What it is saying? One point 1.3. 1.228 means 1. That is the problem. We rounded it off, na? When you round it off, what happened? When you round it off, you will get difference. If it is 1.228, the decimals will be there, na? Then obviously you cannot get exact value. If you take all that perfect, then only it becomes equal to 0. Means nothing wrong, right? So here also I'm writing delta SP is approximately 1.3 to 1.7 times of delta naught. That depends upon why it is giving the range. That depends upon ligand. Right? If ammonia is the ligand, then this gap will be different. If carbon monoxide is the ligand, 6 carbon monoxides are approaching, 4 carbon monoxides are approaching. Then splitting cannot be following same order, no? It may vary. Are you able to understand? That's why they might have given that range. Understood? Say something. Right. Now we are done with square planar, octahedral, and tetrahedral complexes. Any questions? Here ligands should approach. In this case, if ligands approach, say something. Approach along the axis. And number of ligands must be equal to 6. Here also, ligands approach along the axis. Here ligands approach between the axis. Done, sir? Now, this is point number 3. Point number 1, point number 2, point number 3. What point number 3? Field produced by ligands is not symmetrical. If it is not symmetrical, all d orbitals will not be degenerate. Their degeneracy is lost. Now, point number 4. Point number 4. Based upon ligand field strength. So how can I decide ligand field strength? If the splitting gap is high, or if delta naught gap is high, if delta naught gap is octahedral complex only, delta naught means octahedral, right? If it is very strong field ligand, then what happens to the delta naught value? More. If it is moderately strong ligand, means the delta naught values also may vary, right? So based upon ligand field strength, based upon ligand field strength, all the ligands are arranged in one order. We call that order as spectrochemical series. We call that order as spectrochemical series. Once open your target, spectrochemical series. Where? Yes. Page number 19 at the end they have given spectrochemical series, right? Page number 19, huh? Page number 19 at the bottom they have given that series order, right? Which is strongest ligand? Carbon monoxide, where carbon must be the donor, correct or not? Carbon monoxide always carbon acts as a donor. Monodentate ligand, it is not ambidentate ligand, correct? Then CN minus, then ethylene diamine, then ammonia. After that, EDTA, ethylene diamine tetraacetate. Correct, sir? Then EDTA, comma. Okay. NH3, EDTA. Okay, man. Okay, 4 minus. N, don't write that. Better write like this. NCS minus. After that, H2O, then C2O4 2 minus, OH minus, F minus, sulfide, chloride, Cl minus, SCN minus, Br, iodine. That's all. Okay then. Here carbon donor. Here also carbon donor. Here ethylene diamine. Nitrogen is donor. Here also nitrogen donor. Here oxygen donor. Correct? Observe this case and this case, sir, carefully. Okay, man. I am not writing same, right? NH3 is better than EDTA because this is oxygen donor, it is nitrogen donor, right? Now observe thiocyanide and isothiocyanide. Generally, if nitrogen is donor, it should be strong field ligand. Single exception you will find. That statement when nitrogen is donor, strong field, carbon is donor, strong field. In remaining cases, they are all weak field. That is followed by everything except thiocyanide and isothiocyanide. In isothiocyanide, right? Here nitrogen, if nitrogen is donor, then it is isothiocyanide, right? Here sulfur is the donor, thiocyanide. If sulfur is donor, it is strong field ligand. If nitrogen is donor, in weak field ligand. Only in case of isothiocyanide and thiocyanide, there will be difference. Remaining all follows the order of carbon and nitrogen donor strong field, remaining cases weak field ligand. Clear? Response, sir. So only remember these two. So point number 4 is over. Based upon that energy gap, splitting gap, ligands are kept in an order and we call that order as spectrochemical series. Now point number 5. Point number 5. Now see this. If the ligand is very strong field ligand, what happens to this delta naught value? High. If delta naught is high means that gap is high. Now I start filling electrons. I want to fill 7 electrons. Now I want to fill 5 electrons. How to fill it? 1, 2, 3. Now 4th electron. Whether that 4th electron goes here or pairs up, depend upon delta naught value. If that delta naught is less, 4th electron goes to Eg. If delta naught is high, 4th electron will pair up. Are you able to understand? Now I am writing 5th point. If delta naught value is greater than pairing energy, P represents pairing energy. If a delta naught is greater than pairing energy, what happens? Delta naught is more than pairing energy. Then do electron will go to higher orbitals or will pair up? So in this case, pairing of electrons takes place. Any questions? If delta naught is less than pairing energy, if delta naught is less than pairing energy, then response, sir. What is this delta naught? What is delta naught, sir? Can I call it as crystal field splitting energy? Ligand field splitting energy, correct? Crystal field splitting energy. Hereafter, I call this as CFSE. Hereafter, I will call it as CFSE. I will not write as delta naught every time. I will write as CFSE value, right? If delta naught is less than pairing energy, means pairing energy, in order to pair, I have to flip the electron, correct? I have to change the spin of electron. Now we call it as flipping, right? If pairing energy is more, means flipping require more energy. So instead of flipping, what it will do? It will go to E orbitals because gap is low. So what happened? Electrons start filling in. Electrons start filling in higher orbitals. Any questions are in this? Response, sir. Do you have any questions in this? So these are the 5 postulates of crystal field theory. These are the 5 postulates of crystal field theory. Ligands are considered as point charges. Interactions are ionic interactions or electrostatic interactions. Means there is no overlapping of orbitals, intermixing of orbitals, hybridization, nothing is there according to this. Next, when ligands are approaching, repulsions or field strengths are not equal in all directions. Therefore, degeneracy is lost. When degeneracy is lost, the orbitals will split into T2G, EG based upon number of ligands and shape of the ligand, shape of the complex as tetrahedral, square planar, octahedral. Based upon ligand field strength, ability of the ligand to split them, repel that, or make the degeneracy, lose the degeneracy of the orbitals. They have been kept in one order. We call that order as spectrochemical series. Based upon that energy gap, crystal field stimulation energy and pairing energy, by comparing them, sometimes I need to pair the electrons, sometimes I need to fill the higher energy orbitals. These are the 5 postulates of crystal field theory. Now see this. First, I am considering octahedral complexes. In octahedral complexes, which will be having higher energy, EG orbitals will have more energy than T2G. Correct, sir? Now, if the ligand is very strong and coordination number remains 6. Now, 6 strong field ligands are approaching, 6 weak field ligands are approaching. Both are octahedral complexes only. When there are 6 strong field or 6 weak field, both are octahedral complexes. If 6 strong field ligands are approaching, then what happens? If strong field ligands approach, means what about delta naught value? So delta naught becomes greater than pairing energy. If a weak field ligands approach, then what happens? If a weak field ligand approach, then what happens? Then what happens, sir? That is, delta naught will be less than pairing energy. Same thing I am going to study in tetrahedral complexes. Same thing I am going to study in tetrahedral complexes. Are you able to understand what I am trying to draw? In tetrahedral complexes, what about this one, sir? T2 will have more energy than E. Don't write as EG. Huh? Coordination number should not be 6. It should be 4. Now, I need to fill first electron, D1 configuration. Tell me, sir, what I have to do? D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. Right? D10, D1 configuration means 1 electron. Where I have to fill that electron? EG, T2G. Where I have to fill? T2G. So configuration becomes T2G1, EG 0. If it is weak field, then also same only. T2G1, EG 0. Respond. T2. T2G2, EG 0. Here also T2G2, EG 0. Next one. T2G3, EG 0. Here also T2G3, EG 0. Now problem solved starts. T4. Fourth electron. And T2 means 3 boxes. 1, 1, 1 electron I have filled. Now, do the fourth electron will pair up or goes to higher orbital? Because gap is more. Here, less. So if it is less, it goes to higher. If it is more, will pair up. So what is the configuration now? T2G4, EG0. Here, T2G3, EG1. Next one. T2G5, EG0. T2G3, EG2. T2G6, EG0. T2G4, EG2. Respond. Correct or not? Next one. T2G6, EG1. T2G5, EG2. Next. T2G6, EG2. Here also T2G6, EG2. Respond online.
Yes, sir.
Yes, sir.
Yes, sir.
Done, sir. Now what about CFSE value? Up to here it is okay. What is CFSE value? When electron occupies in first orbital for T2G, what is that energy? Minus 0.4 delta naught. Let's see, man. Octahedral complexes. If I start filling electron here, each electron's energy is minus 0.4 delta naught. Correct or not? So what is that CFSE value here? Minus 0.4 delta naught, minus 0.8 delta naught, minus 1.2 delta naught. Now minus 1.6 delta naught plus P. Why, sir? Electron got paired. Correct? Plus pairing energy. Now 2 delta naught plus 2p. Now 2 electrons got paired up. Next one, sir. If you are able to give this, for sure you will get A rank. D6. What is that CFSE value? Minus 2.4 delta naught plus 3p 2p only. Minus 2.4 delta naught plus 2p. 3 days back, I am taking one demo on madam from IIT Mandi, NIT Mandi, IIT Mandi. She gave demo on CFSE, right? She wrote all these values. She keep on writing. I asked, I don't want all this, madam. Write only in case of D6. Only one question I will ask. If you are able to answer this, I will not ask any other question. If you are unable to answer this one, I will ask the next question. Second question also I said the same. What is hybridization of CF3 radical? Again, my question is same. If you are able to answer this, I will not ask any other question. Otherwise, I will ask third question. Right? In that way, I asked 7 questions. Right? Now, again, same question for you. 2.4 delta naught plus 2p. Why I wrote 2p? Why not 3p? Huh? What is D6 configuration, sir? Before splitting. What do you mean by D6? Already one electron already paired in D6. Correct or not? Already that pairing energy is there, no? Respond. Now after splitting, 3 got paired. Before splitting, 1 got paired. Now what is the gap? 2. Therefore, I have to write it as minus 2.4 delta naught plus 2p. Is it clear? Next, sir. Next, sir. Next. Minus 1.8 delta naught. Array, 1 electron is there in EG. Means plus 0.6. Correct? Plus 0.6 means it becomes minus 1.8 delta naught plus how much pairing? In a D7, how much already paired? 2. Now how many paired? 3. So difference. Next, sir. Minus 1.2 delta naught. Correct? I will not write anything. D8, how many paired? In a D8. Before splitting 3. After splitting also 3 paired. So there is no pairing energy. Respond. Next one. Minus 0.6 delta naught. And finally 0.00 delta naught. Clear? Right? In this way, by tomorrow, fill remaining all. Right? So we are done with next concept. What is it? Crystal field theory. Right? Tomorrow we will complete that and we will go to next concept. Response, sir. Next concept is color of complexes. Right? So hardly we have. Listen. Hardly we have color of complexes, one concept. Organometallic complexes. Then metal carbonyls. Stability of complexes. Then applications of complexes. If you discuss 5 more topics, coordination compound chapter is over. This is CFSE and valence bond theory, hybridization and CFSE and geometry. What do we call that? Isomerism. These 3 are heart of this chapter. 99.99% cases. If they ask you any questions from coordination compound chapter means, right? One question they must have to ask from isomerism. Another question they have to ask from either VB theory or CFSE. Crystal field theory, CFD, right? For sure, in any paper, you will get 2 questions from coordination compound chapter. Clear? Whether it is mains or advanced. If you are lucky, in advanced paper 1, they may ask 2, paper 2 also 2, if you are lucky, right? Whether you are lucky or not, for sure you will get 2 questions, 1 in paper 1, 1 in paper 2, or 2 in paper 1 or 2 in paper 2. For sure you will get 2 questions in advanced. Mains also for sure 2 questions. Clear? So I will stop the discussions are online. Any queries do you have?
No, sir.
No, sir.
No, sir.
Right, sir. I will end the session. Array, one more thing. Tomorrow, I will have 3 classes. Mentally prepare for it. Okay? At any cost, tomorrow I need to close coordination compound chapter. At least I need to keep the heading alkyl and aryl halides. Reason, weekdays, I am about to complete alkyl and aryl halides chapter. Next week, I will complete that chapter and I will start alcohols, phenols, ethers also. You are behind by 5 lectures compared to them. Right? Means 1.5 weeks almost. Okay, wow. Alcohols and phenols, from that chapter also, half of the reactions already I completed in weekdays. Right, sir? Yes, sir.
So notes for coordination compounds, can you post?
I already posted notes for coordination compounds. Weekdays notes I already posted.
No,
Array,
sir.
say yes or no. I already posted in your channel. Once I have done that chapter for weekday students, I already posted. In next week, I am going to complete this chapter also for them. That notes also I will post in advance. Right? Remember, if alkyl and aryl halide chapter is over means, every week I will complete 1 more chapter. Alcohol, phenols, ethers, 1 week. Aldehydes, ketones, 1 week. Amines, biomolecules, 1 week. Both put together 1 week. Polymers, chemistry in everyday life, 1 week. Over. By that time on Wednesdays, I will complete metallurgy. Surface chemistry almost over, man. This week, this Wednesday, I will complete surface chemistry. After that, metallurgy. What canceling? Every week they will create new channel, new link, man. Right? Every week they will create new link. You join in that link. Right, sir? Again, this coming Wednesday also, you have. Yes, sir.
So this chapter notes is actually not there in Teams.
Not
Only
there.
up to it's there.
Hey, please.
Only till oxygen family it's there.
Correct? (25-26) coordination compounds. I posted these notes on 25/7. Okay. Oh, I am not able to upload notes, man. Hey, already uploaded. Yes. Done, sir. Now it is available. Right, sir. Online students, I will download your attendance. Wednesday, don't try to miss the class. Right? Try to attend at least. Okay, I am closing the session, sir. Bye.